So in the previous demo, you found that the code did not work. For example, if you have seen, my B008 should have been 3 and my B000 should have been ECAD and D200 should be BABE and D208 should be CAFE. All this did not happen. So why it did not happen? So let us go. This is just an exercise. We had initialized stack pointer to 0, and it's a segment when you try to push in, then if the stack pointer is 0, then when you try to push, it basically gives a stack fault, and that is why it was not able to. And when we actually have an interrupt, the stack is being pushed into, and so essentially nothing could move into the stack, and that is the reason why the program did not work. Now we go to line number 52 and make it 0x50, and we will also see in your another window here lab2.s, and go here and see that this is, go down to that particular line, and you here see that your move esp, 0x50. So once you do this and compile this and then upload this here, now let us go and check what is there in B1000. There is some value, and of course all are null characters in B1008. Now we continue. Now you see what is there in B1000. It is ECAD. B1008, it is 3. That's what we wanted. And we'll check the other values also, as we see here. B1020. B1020. There's been F. 30 is DF. So 8 is 3, we have already checked. D200 is B. D208 is CAFE. So this basically worked. And let us also now see where does the stack start. Essentially the stack is starting at B1100 and we are looking at 50. So let us see S/10x 0x B140. So now as you see here, there are things that have been pushed here, 46, 8, D8. So this was the code segment, etc. So the stack is now operational at B150. So the stack actually grows down. So initially when we made ESP as 0, it basically started growing down beyond B1100 and essentially it became negative. Now when I made ESP as 50, it started working with 4F and B14F, as you see here. This is where the stack has been operational. So what we have done in this assignment is we have created 3 faults. One is an hardware generated fault, divide by 0. The next one was an overflow, where there was an overflow created and then an into instruction was executed to see the overflow. And then there was a software defined in31. The difference between the first and the last two was that when the interrupt service routine completes its execution, in the first case divide by 0, it came to the same instruction that created the fault, so that we could actually rectify. But in the case of the other two, it went into the next instruction that actually created the interrupt, and this is very important to be noted. So interrupt service routines, which can be potentially a big source of uh, uh, security vulnerability, because that actually causes multiple privilege level changes, as we will see in the subsequent assignments. But so what we have done in this particular assignment is to basically demonstrate how you write interrupt service routine, how you load the IDTs, and how you configure this. So this what I suggest that is, down the line you please start generating more interrupts that you see in the Intel manual, and uh, and write some interesting interrupt service routines. Right? Please note that the major part of servicing device request comes from an interrupt service routine. The device driver actually forms a major component of the interrupt service routines. So it is very important that you understand this particular assignment, and I hope you have done so. Thank you.